On slide 23, we turn to examples. And we're going to work with 3 examples from the Ort et al. Article concerning depression and self-esteem. And we have a nice spread of sample sizes, a number of time points, and intervals between the measurements in these data sets. The MWI, my work in I data that we mentioned, that we used to inspire our Monte Carlo simulation, has 663 individuals, 5 time points, and our measurements are with 2-month intervals. Then we have the BLS data, n equals 404 with 4 time points and interval 1 year. And then the LSY data, where you have a much larger sample size, 8,259, and many more time points, 11, with a 2-year interval. So that'll be interesting to see which cross-lagged effects survive these long time intervals, and for which data sets we need to have lag 0 and reciprocal interactions. A 4th data set is the depression and disability data that Ormel and others worked with in their 2002 article. So here we have 753 people, only 3 time points, the minimum, and the interval is 1 year. Finally, we're going to look at academic self-concept and achievement, where the sample size is 933 with 5 time points and 4-month interval. So turning to slide 24, let's take a look at the first example, the MWI data on depression and self-esteem. So this is an adult sample, and we mentioned the N and the T, and we also note that the coverage varies over time. Coverage meaning non-missing data, that is, first time point, the variables are measured for 99% of the sample. The last time point is only 57% of the sample surviving. So we have attrition here. Self-esteem and depression are measured 2 months apart. And for self-esteem, participants were asked how much they agree with each of the statements included in the scale. So in this case, there is no time frame stated. So one can imagine that this answer draws on both current and past experiences. For the depression variable, they were instructed to assess how frequently they had experienced a set of symptoms within the preceding 30 days. So there it's more explicit what the time frame is. We're going to try an RI-CLPM with time invariant cross-lagged effects, the traditional RI-CLPM, and that points to a small but significant cross-lagged effect of depression on self-esteem, as Ort found and shows in his table 6. So effect of depression on self-esteem, that is regression of self-esteem on depression. Now turning to slide 25 then, let's think a little bit more about which estimators we should choose. We can use MLR, maximum likelihood with robust chi-square and standard errors. And that's needed because we have data, in this case, that have non-normal distributions for the outcomes, quite skewed variables. So to get reliable chi-square and reliable standard errors, we use MLR. The drawback is that we don't get non-symmetric confidence intervals, which might be needed for the reciprocal effects. I mean, note then, as a reminder of how Mplus is set up, the MLR parameter estimates are the same as the maximum likelihood parameter estimates and are the same as the parameter estimates using Bootstrap. So Bootstrap only influences the standard errors. Now, Bootstrap analysis uses the ML estimator in Mplus. You have to say ML estimator equals ML. And it gives the Bootstrap standard errors and Bootstrap non-symmetric confidence intervals matching a skew distribution for these reciprocal estimates. The Bootstrap standard errors are a little bit inflated, as we saw in the Monte Carlo studies. So the CIs, the confidence intervals, will be a little bit too wide, conservative. So what I do here then is do 2 runs, one with MLR to get chi-square and standard errors, and one with Bootstrap to get confidence intervals. Slide 26, then we have the Mplus input for this new reciprocal RI-CLPM model for the MWI data. MWI, I should say. So we have here the usual Mplus setup with the title and the data and the variables. ID being the indicator of the person. So we have certain missing data flag -999, and then in the analysis command we have the estimator option set to ML, which we use for Bootstrap, as I'm saying here in the comment. And we have the alternative of using MLR for chi-square instead. By continuing with the ML estimator, we ask for 500 bootstraps. That's usually sufficient in these situations. You can try 1000 and compare for yourself. And we're going to ask for starts equals at least 20 for these models. We need to be sure that we get the best log likelihood. And then we come to the model, and first we specify the random intercept, one for the self-esteem variable IS, measured by those 5 outcomes with fixed loadings 1, and same thing for the random intercept for the depression measure. And then we come to the autoregressive part, and here we then introduce again the new feature in Mplus. We're using these hat variables, S2 to S5 hat, D2 hat to D5 hat. And that's explained in Webtalk 4, part 1. And these hat variables represent those within variables in circles that I showed you in the initial early model diagrams. The hats denote residuals, so they are residuals. If you think about it this way, you have IS measured by the S variables. So the S variables are regressed on IS, and what's left is the residual, which is the hat variables. So therefore there's no need for creating within factors using by statements. So this saves specification lines and time. And then we continue in the right column here. The cross-lagged effects then are S for time point 2 regressed on D on time point 1 with hats, and P on here, this is the pairwise on, and likewise the other direction, D on S. And then we come to the new feature, the reciprocals. So here we have the S2 on D2 all the way down to S5 on D5. And we hold them equal across time. I'll just call that reciprocal for S and regressed on D, and likewise D regressed on S, RDS. So we have we estimate 2 reciprocal coefficients, holding both of them invariant across time. And then we note that we correlate the first time points residual variables within variables, but not the remaining time points. That's important to keep track of. And then in the model constraint section, we have 2 alternatives. We have restriction A and restriction B. And to remind you, restriction A ensure that we get positive R square and we avoid the dual solutions. So that's the product of the reciprocals should be greater than 0, and the product should be the difference from 1 should be greater than 0. That is, this product is less than 1. If you want to think about it, you can move this product over to the left side, changing signs, and it'll be less than 1. So it keeps it between 0 and 1, this product. Restriction B, you have the non-duality, and there it is the square of the product minus 1 that is less than 0. And then we come to the confidence intervals. So we use a Bootstrap confidence interval. So we look for that in the output. Now, we're going to be focusing on these three key models that we have talked a little bit about earlier. And here we draw them for the within part of the random intercept version of these models. And we see that we have 5 time points. At the top is the standard RI-CLPM. In the middle we have the reciprocal only model, where we leave out the cross-lagged effects and instead have the reciprocals here. We keep the residual covariance across time, like we have in the RI-CLPM. And then the bottom model, model C as I call it here, is the reciprocal model. That is, it has both cross-lags and reciprocals, but it doesn't have the residual covariance that is not identified on top of the other parameters. So you have 3 major choices, and then within each set of these 3 models, A, B, C, you have variations of how much invariance you want to hold across time. Now if you go back to slide 26 then for a second and think about this, how do you get the regular RI-CLPM from this input? How do you modify it? Well, RI-CLPM does not have these reciprocals here. So you just comment, you can just comment out the reciprocals, but then you would have to add the residual covariances here for each of the 5 time points, not only the first one. That would give you model A, RI-CLPM. Now model B, the reciprocal only model, would get rid of the cross-lag section, comment that out, and estimate reciprocals here. But then you would have to once again add the other 4 residual covariances, because when you don't have the cross-lags, you can identify the residual covariances. So you want to have them in the model in line with how it's shown here for model B across time. So with very easy manipulation here, you cover all 3 models. And then again, you can have various degrees of time invariance. Putting a label here for the cross-lags, hold them invariant across time, 1 for each of the 2 types of cross-lags. So there you have it. Now, on slide 28 then, let's look at the model fit for these 3 random intercept models. Model A, Model B, and Model C. And I'm just doing this from a pedagogical point of view, showing that they are equivalent. That is, they have the same number of parameters, same log likelihood, same BIC, etc. And in this case then, what we've done for the reciprocal model, the bottom model, we're imposing the T-1 restrictions, that is 4 restrictions, and we are only estimating 2 equals 3 and 4 equals 5 reciprocal coefficients. So that's the invariance approach that we can take to make model C equal to model A, and is also equal to model B. Model C uses now here, as presented here, restriction B of non-duality, and it gets 2 negative R² values for the within part relationships. So that solution should not be used. Now if you use the recommended restriction A of non-duality and positive R², then you get a worse log likelihood, minus 1535, worse than minus 1532, and BIC goes up to 3357 instead of 3349. So the equivalence with model A is lost, but it's a perfectly okay model in itself. So this can happen, and you have to keep track of this. If you want to go for the equivalence, then you may, in some cases, and only impose restriction B, then you may get negative R-square values. So you should look at the standardized solution at the bottom of the estimate to see that you don't have any negative R-square values. You don't want to have that. Now, model C can also be done ignoring this equivalence with the other two models. Can be done with fully time-invariant reciprocals. So using only 2 instead of the 4 reciprocals that we have in this model C up here. So using only 2 reciprocals, 1 for each direction, that gives you actually the same log likelihood in this case for these data, 1532, with 2 fewer parameters, and therefore a better big value. So we show that model on the next slide. So it's interesting in this case, with some perhaps luck, with fully time invariant reciprocals, a natural assumption, we get as good of a likelihood as the other two models, and therefore that model wins on big. So here then on slide 29, we are looking at a series of models, and we're going to add even more to this list. So once again, we have the RI-CLPM with 44 parameters, and we also recognize the reciprocal only model with 44 parameters and the same fit statistics. Now, for the RI-CLPM, you can add invariance, time invariance of the cross lags, and you get fewer parameters, six fewer parameters, and you will get a difference in log likelihood by 14 points, 8 plus 6. So that's let's see, that's this is also MLR estimation here. Now we should remember, which means that it's you have to take into, for a strict difference, chi-square difference test, you will have to take into the scaling correction factor. But in this case, it looks like with a difference of 14, which you double then, it's a 28 with 6 parameters, looks like it's a significant misfit adding the invariance of the cross lags. Now for the reciprocal only model, you can try the reciprocal only model with invariance of reciprocals. In there you again have 6 parameter difference. But here the difference in log likelihood is only 6. So the 2 times log likelihood difference is 12 with 6 degrees of freedom, so to speak. If we ignore the scaling correction factor, it doesn't seem to be that bad of a that much worsening of the fit by adding the invariance of the reciprocals. Now the reciprocal model with invariant reciprocals, the one we alluded to at the bottom of the previous slide, has 42 parameters, 2 less than the model A here, model B here. Here's model C. So the log likelihood happens to be the same. So of course that gets a much better, or not much better, but a better big value. And the p-value for the chi-square test is now for the first time above 0.05. RMSEA is pretty good for all of these models. And then you can go further. Model 6, the reciprocal, invariant X lags, and reciprocals. So you're adding the invariance of the cross lags here, getting you down to 36 parameters. Log likelihood worsens a little bit. So the difference here is that you add the cross lag invariance. You have 6 degrees of freedom difference here, and it's only 714. So once again, Model 6 does not seem to worsen the fit of Model 5 with that much. Maybe fairly significant, but it's not by much, practically speaking. And our model gets the best BIC value here of all of the models. And since several of these models are not nested, BIC is an important factor to look at. So once again, Model 1 is equivalent to Model 3. Model 1 is also equivalent to a reciprocal CLPM, with reciprocals restricted to equality, for instance, for times 2 equals 3, 4 equals 5, which implies that comparing Model 5 to Model 1 tests for full reciprocal invariance. You know, that's the difference. Model 5 is therefore not rejected in that difference investigation because they have the same log likelihood. They even have the same log likelihood. All right. Slide 30 then takes a look at the Bootstrap distribution of the reciprocal effects. And in this case, it's self-esteem at time t influencing depression at time t. So this is a lag 0 effect, contemporaneous effect, and it is a key effect that we find for these data. So it's a reciprocal RI-CLPM with time invariant cross-lag and reciprocal effects. So it's Model 6 on the previous page. And the Bootstrap distribution, we see that we have a little bit of a skewed distribution perhaps, but most importantly, we have a big mass here around the peak, minus 0.4, saying that increasing self-esteem decreases depression at the same time point. Increasing self-esteem decreases depression at the same time point. But it's not quite significant because the 95% confidence interval goes from minus to plus, so it covers 0 here, and therefore would indicate non-significance, but it's close to significant. And we will see that it becomes significant in a forthcoming analysis. Model 7. Now looking at the effect going the other way, depression influencing self-esteem, in that same model, the peak is around 0, and it's also insignificant. But the peak and the mass of the distribution here, Bootstrap distribution, over the 500 draws is 0. So this indicates that the parameter can be fixed at 0. So continuing with the fit table then, we were down here, Model 6. From Model 6, looking at the results, we will add the restriction that we only allow S influencing D, but D influencing S is fixed at 0. And this model gets an even better BIC value. So that's a model you may want to stay with. And just to test this out, let's use the same model but allow only the effect in the other direction. Same number of parameters and a worse fit, worse log likelihood by 6 points, and a worse BIC, and a worse p-value for chi-square. So Model 7 seemed to be a reasonable model to consider here. So on slide 33, we have a summary of the analyses. We're looking at the estimated effects in 3 key models for this data set. And several of these models fit the data about the same as we've seen, but have different interpretations. So here we have the 3 major contestants. Model 2, we're using the invariant X-lag version of it for simplicity. So that's the model type A, and then model type B is the reciprocal only model with invariant reciprocals, and then model type C our key model type reciprocal with X lags that are invariant, and the reciprocals are invariant as well, plus we restrict ourselves to allowing only the contemporaneous lag zero effect in one direction, fixing the other one to zero, as indicated by the previous slide's analysis. So looking at this then, we see interestingly that the model 2 here gets a significant cross-lagged effect. Depression when depression increases, self-esteem at the next time point decreases. For that model, we don't have reciprocals, so that's not applicable. For reciprocal only, the cross-lags are not available, so that's not applicable, not available. And the reciprocals turn out to be non-significant. Model 7 then, we actually find the same cross-lagged effect as for the RI-CLPM. Similar estimates, in fact, as well. But we also find a significant reciprocal effect from self-esteem to depression. So when self-esteem goes up, depression goes down, talking about the same time point. So that's an interesting extra information that Model 7 gives beyond Model 2 up here. And for this reciprocal effect, we should also point out that we want to look at the Bootstrap confidence interval here, because reciprocals tend to have non-normal distributions. So we would look in the output section called confidence intervals of model results to make sure that the confidence interval doesn't cover a zero, but you have significance. So I would say Model 7 may be preferable here because it is more informative than the others, and it contains Model 2 as a subset and doesn't really fit worse. And Model 7 has the best BIC, and BIC is useful here, as I say, because the three models here on the screen are not nested. And again, standardized cross-lagged effects for models 2 and 7 are very close. So here I would say that you do get more information by looking at the reciprocal cross-lagged model. And it'll be interesting to see now if that holds up for the other 4 data sets. So looking closer then at Model 7, what it says on slide 34, let's look at the indirect effects that this model implies. And we're looking at only 2 time points, the 4th and the 5th. And we're looking at standardized estimates and Bootstrap confidence intervals to decide on significance. So using model indirect then, we can look at the effect of S4 to D5. S4 to D5 has a direct effect, but that was not significant. But S4 influences D5 also indirectly, and by 3 different, well, first of all, the total indirect effect is minus 0.339, so it's non-negligible, and the Bootstrap confidence interval does not cover 0, so it's significant. And that consists of 3 different paths, S4 to S5 to D5, which is the major part, minus 0.223, but also S4 to D4 to D5, which is minus 0.092. And the effect, however, from S4 to D4 to S5 to D5, let's see, S4 to D4 to S5 to D5 turns out to be insignificant by the Bootstrap confidence interval. The direct effect, as we said, S4 to D5 is insignificant. So you can decompose the effects this way, And of course you can go all the way back to the first time point if you want to see the effect of one of the variables on the other variable at later time points. You can also look at the opposite, the effect from D4 to D5, for instance, is positive 0.250. As you would imagine, it's positive. And the indirect effect, D4 to D5, is 0.051. It is small but significant, does not cover 0. D4 to S5 to D5 is pretty much the whole indirect effect. It is the whole indirect effect, so same values. And then the direct effect, the autocorrelation, autoregression is larger, of course, large as usual. So this is a way to interpret this lag 0 contemporaneous RI-CLPM.